All right, so this is going to be the video for the zeros of polynomial functions. You can see that I color-coded different pieces of the graph, and so I'm using that color coding to go over this with you. So let's first take a look at this graph of f of x, and let's look at the end behavior, the left side, which is red. This is as x approaches negative infinity. F of x, because that's the name of the function. And look at what it's doing. It is falling left. So the y values are going to negative infinity. So now let's take a look at g of x and look at the left behavior. Look at where the red arrow is going, right? As x goes to negative infinity, g of x approaches positive infinity. Now let's take a look at h of x. As x approaches negative infinity, and again, this is the red, h of x, which is the y value, approaches negative infinity. All right, now let's take a look at the green. As x approaches infinity, f of x approaches positive infinity. You can see that it's rising right. On g of x, we can also see on the green that it is rising to the right, which is indicated by infinity. And then also on h of x, that is also rising to the right. So it is going towards infinity. And so what we have next are the zeros. So you can see the blue dots. Those are the x-intercepts. So x is equal to -2, -1, and 1. On g of x, x is approximately -2.5. We don't know for sure. We don't have an equation, so we can't justify that that is exactly 2.5. So we're saying approximately. And x is equal to 2. And on the last graph, we have x is equal to -4. We've got x is equal to -2. We've got +2 and 5. So this next piece, which is to define the multiplicity of a zero. So let's just make sure we understand that. The multiplicity of x equals a as a zero is the number of times x minus a is a factor of the function. All right, so like if we did a warm up last week with that. So if I said x minus a to the third power, that's going to be a multiplicity of 3. All right. So now it says to read the following information about the multiplicities of the zeros of f of x, g of x, and h of x while studying the graphs above. Then we're going to answer the questions on the next page. So let's take a look at the graph of f of x. F of x, all of the zeros have a multiplicity of 1. So let's just make sure that we take a look at that. All of the multiplicities are 1. In the graph of g of x, though, the zero of x equals -2.5 has a multiplicity of 1. X equals 2 has a multiplicity of 3. I want you to look at the multiplicity of 3. I've done this in orange, and you can see that I'm referring to it as a point of inflection. That's what you guys have previously maybe heard of, the word chill, but the proper academic vocabulary is point of inflection. And then in the graph of h of x, the zeros here have a multiplicity of 1, and x equal 2 has a multiplicity of 2. So let's take a look at what that means. So we're going to go into the proper vocabulary for that. So this is when it bounces back, it's the point of tangency. That's because when you're tangent to something, you only touch it, you don't cross it. So you touch it only at one spot. All right, so now let's take a look at the questions over here. Number 1, what do you notice about the sum of the multiplicities of the zeros and the degree of the function. So let's take a look. We could take a look back here at the graph. We've got, now we don't know the specific graph, but we've got 3 zeros here. We've got 1 and then 3 here, so that's 4. We've got 1, 2, 3, 4, 5 there. So really the degree is equal to the sum of the multiplicities of the zeros. So that's going to be important for you to make sure you fully understand. Number 2, describe the behavior of the graph as it approaches a zero whose multiplicity is 1. So in other words, what's happening when you have a multiplicity of 1? Well, the graph is going to cross the x-axis and will not change concavity. Let me just introduce you really quickly to concavity. When you are looking at concavity, there's a couple of situations. Kind of think of it as a cup. When you are whether or not you could have an upward cup or a downward cup. And so let me just show you this here really quickly with 2 different colors. This is concave down. Okay, the first one is concave up. So this right here that I'm trying to color code for you is concave down. And now we're going to go concave up. And so now we go concave up. So if you can kind of take a look as if you were to take a teacup, you could see that the teacup would be right side up here, but it would be upside down on this part right here. So we'll get into more of that a little bit later. It doesn't change concavity, which means it's not going to change the type of direction on the graph. So that's kind of like a cut. So on number 3, describe the behavior of the graph as it approaches a zero with multiplicity 2. This is kind of like what your bounce is, right? So it's hitting it and it's coming right back up. Okay, and so on that regard, the graph is going to be tangent to the x-axis. This is what you guys refer to as your bounce. Oh, hold on. Got a little lag here today. So we've got a bounce. Okay, and then that's what's happening here with this point of tangency. Okay, it's got a multiplicity of 2. So on number 4, it says describe the behavior of the graph as it approaches a zero whose multiplicity is 3. So the graph is going to cross the x-axis and it will change concavity. And so that's what's happening here at the point of inflection. It's changing concavity. All right. So now moving on, for each of the following functions, you are given a factor of the function. We are supposed to identify the zero associated with the given factor, then use synthetic division to determine how many times the given factor is a factor of the function, then identify the multiplicity of the root associated with the factor. So let's take a look at this. We know that the factor is x plus 1, so our root is x equals -1. So we need to synthetically divide. So what we're going to do is synthetically divide this polynomial here. So we've got 1x cubed, 2x squared, -1x, and then -2. So I'm just going to perform my synthetic division. And you can see that my remainder is 0. Well, that's because I already know that it was a root. So now what we're going to do is we're going to take this over here. I'm going to change colors for you guys. We're going to take this new function, and we are also going to synthetically divide by -1 with the new function, 1, 1, -2. And we're looking to see if we get a 0 or not. So 1 times -1, we get 0. We get 0, we get -2. That is my remainder. So that is not a 0. All right, so that means this -1 only has a multiplicity of 1. And so now we're going to describe the behavior of the graph. Well, if it has a multiplicity of 1, we can kind of go back up here to the top and look at how we should describe that. So we're going to say that the graph will cross the x-axis without changing concavity. Okay, let's take a look at h of x. So now we have our equation with this. The factor is x is equal to -1. So again, we're going to do synthetic division. I'm sorry, x is not equal to -1. X is equal to 1. So we are going to do synthetic division on this polynomial, making sure that we are writing everything down in proper standard form. And then now I'm just performing my multiplication. And we already know that this should have given me a 0 because we already knew the root was 1. So what I'm going to do is change colors now with this. And I'm taking it here. And we're going to see if it has a multiplicity again. So we're going to get 2, 1, and -3. And then this gives me a 2, that gives me a 3, and look at that. So it is a 0. So that means I need to keep going, because what if there's, what if they're all 3 the same, right? Remember, I have x to the 3rd power, so I have 3 zeros. So what if I have that there? So I need to do it again. So I'm going to 1, and then I'm going to go 2, 3. And then that gives me a 5, and so that's not a 0. So that means there's only 2 that worked, so that 1 has a multiplicity of 2. So that means it's going to have that bounce. But again, we don't want to use that academic word bounce, right? Because it's not really an academic word. We're going to use tangency. So we're going to say the graph is tangent to the x-axis at x equals 1. Okay, now let's take a look at this one right here. We've got a root as x equals 1. So let's go ahead and try this. It's in standard form. So we've got -1, 1, 3, -5, and 2. And I'm just going to perform my synthetic division. So we already know that this is a 1. It's kind of what we were given. So now what we're going to do is do it again, but with this information, right? So -1, 0, 3, -2. Okay, we're taking this and we're doing it again. So -1, negative. I gotta not be so careless here. All right, and so that's another 0. So what we're gonna do is try again with, I guess we'll do a different color this time. Let's do red with this information here. So -1, -1, 2. Oh, look at that. We have another 0. Wow. So that's already 3, but now we need to continue to go on a little bit further. So let me just take 1 and take this information, -1, -2. Gives me -3. All right, so finally what we have are, we have our graph here with a multiplicity of 3. And so remember when x is equal to 1, so we won't always have a graph, but that's what's happening. We have a multiplicity of 3, so the graph is crossing. Graph is crossing the x-axis, and it does change concavity. And it changes concavity. And again, I'm just taking that word, that description from right here. So I'm taking the descriptions and bringing it right back to that. All right, so now let's consider how we might be able to locate the zeros of a polynomial function numerically. All right, so we have our function h of x, and we need to be able to, here's the graph, right? Find each pair of function values in the table below and answer the questions that follow. So what I need you to do is actually calculate h of -2, like plug in h of -2 and evaluate that. You can use a calculator, but if you were to evaluate that, you're going to get a -9. And then h of -1, if you were to plug that in, I believe you're going to get 4. And then let's also do that since we're on a roll. Let's evaluate h of 0, which should give us 3. And then h of 2, again, you can plug that into the function and do your algebra, but you should get 7. So now it says from the graph, clearly h of x has a 0 between -2 and -1, right? We know that it crosses there, okay? Explain how you're finding the values of right here, h of 2 and h -1 above numerically shows that there is a 0 that exists between -2 and -1. Well, if you're going from negative to a positive, that alone is going to tell you that you're crossing the x-axis. So let's look at how we can write that. Since h of -2 equals -9 and -9 is less than 0, the graph of h of x is below the x-axis at x equals -2. Since h of -1 equals 4 and 4 is greater than 0, the graph of h of x is above the x-axis at x equals -1. H of x is continuous between x equals -2 and x equals -1. First, because all polynomial functions are continuous, just in case you didn't know that, and goes from below the x-axis to above the x-axis, guaranteeing a 0 exists between -2 and -1. So now let's take a look at this one. Does the same reasoning that you described concerning the 0 between -2 and -1 hold true for the existence of a 0 between 0 and 2? Now notice 0 and 2. We have a positive and a positive. So it says since h of 0 is 3, 3 is greater than 0, and h of 2 is equal to 7, and 7 is greater than 0, the graph of h of x is above the x-axis at 0 and 2. This does not guarantee the existence of a 0 between 0 and 2. However, there is a possibility of a 0 whose multiplicity is 2 or 1. So we will get into that, but just because the signs are the same, that does not guarantee that you have an actual real 0 that will cross the x-axis. You can kind of think of this as a counter example here. If I had the same thing where this is 0 and this is 2, you can see that there was a turning point, right? But that does not show that there is a 0 that crosses the x-axis between 0 and 2. So we have to be careful of that. So let's take a look over here. And it says, based on what we've just seen, what inference can you make about the existence of a zero of a polynomial function if you know the value of the function at two different x values? So when I say two different x values, we can say, well, if x is equal to a and x is equal to b, those are two different x values. So if f of a and f of b have opposite signs, now this is the x values would be a and then b. F of a is the y value and f of b is the y value, according to each x. So if the y value when x is equal to a and the y value when x is equal to b have opposite signs, a zero of multiplicity 1 or 3 is guaranteed to exist between a and b. However, if f of a and f of b have the same signs, which you just looked at a second ago, a zero of multiplicity 1, 2, or 3 is possible to exist between a and b. And now we're just dealing with possibly imaginary roots and so forth. So let's take a look at this table value, and then then we'll be done. The table of values below represents values of a quartic function, so x to the fourth, which means we're going to have 4 zeros. The function has a negative root and two distinct positive roots. All right, now we're going to answer the questions that follow. Number 1, is there any or are any of the roots f of x specifically identified in the table? So if we can look for a root in the table, let's look at this y values. Remember, if it's a root, it's going to have a y value of 0. And then what is the multiplicity of the 0? And explain your reasoning for both questions. So x is equal to 1 is a 0 of f of x, because when x equals 1, y is equal to 0. Okay. Since f of x is a quartic function, the sum of the multiplicities of the zeros cannot exceed 4. The y values change signs twice. Look at that. They change here, and they also change here. So that's going to be a 0 here and a 0 here. That's 2 zeros. Here's a third 0, but we need 4. All right. Therefore, x equals 1 must have a multiplicity of 2. Here's why. The y values do not change signs on either side of x equals 1. Notice how they're negative here and they're negative here. So that's going to infer that that's a multiplicity of 2. All right, so it says between which two x values in the table is the negative root located? Well, we've got a negative root in between -4 and -1. So here's how we're going to explain our reasoning. The negative root of f of x is located between x equals -4 and x equals -1. Because f of -4 is positive 40 and 40 is greater than 0, and f of -1 equals -8, and -8 is less than 0, which means the graph must cross the x-axis between x equals -4 and x equals -1. All right, so now we're on to number 3. Between which two x values in the table is the second distinct positive root located? And explain your reasoning. And again, we're going to go from when they're changing signs, a -5 to 26. So you can take a look at here. The second distinct root of f of x is located between x equals 3 and x equals 5, because f of 3 is -5 and -5 is less than 0. F of 5 equals 26. 26 is greater than 0, which means the graph must cross the x-axis between 3 and 5.